Limiting reagent calculations. This is kind of the meat and potatoes of the stoichiometry chapter here. It's also kind of like the iconic high school chemistry lesson, the one that kind of is most memorable for students coming away from their high school chemistry experience. Now, we'll deal with limiting reagents or reactants. We'll deal with the reagent in excess. We'll deal with the theoretical yield. So we'll also deal with like percent yield calculations. All of these will be encompassed in this lesson. Now, if this is your first time joining me, my name is Chad, and welcome to Chad's Prep, where my goal is to make science both understandable and hopefully even enjoyable. Now, this is my high school chemistry playlist. I'll be posting these lessons weekly throughout the 2020-21 school year, so if you don't want to miss one, subscribe to the channel, click the bell notifications. You'll be notified every time I post a new lesson. All right, so if you look at what is really at the basis of these limiting reagent calculations, it's actually not difficult. It's not difficult conceptually. It's something you can see in your everyday life, but the moment we start applying it to like molecules and compounds and things of a sort, it gets complicated in a hurry. And it's things that are a little bit abstract that you're not used to seeing, and you're not used to visualizing atoms and molecules in your head and stuff. So before we apply it there, we're going to apply it to a little more tangible example here. And we're going to talk about building bicycles. So I'm going to quit my job and I'm going to go to local junkyards and I'm going to collect bicycle tires and bicycle frames, and I'm going to make recycled bicycles. That's what I'm going to do. And every recycled bicycle requires 2 tires and 1 frame. And so I've written it kind of like a chemical equation here. So a couple questions I might ask you is, well, if I've got 10 frames, how many tires do I need to convert all of the frames into bicycles? Okay. And probably doing this in your head, you didn't need this chemical equation to see that, but I can see from the chemical equation that every 1 frame requires 2 tires to make the bicycle. And so in this case, if I've got 10 frames, that 1:2 ratio tells me I'm going to need 20 tires. So the way we'd actually formally do the dimensional analysis here is we'd put frames on bottom, we'd put tires on top, and we'd just use the coefficients as the conversion. Every 1 frame requires 2 tires. Just like so, we put frames on bottom so they'd cancel, tires on top because that's what we're trying to get to. And what you probably already did in your head is just said, I need 20 tires for 10 frames, Chad. It's a bicycle. Sweet. And I'm hoping it's that simple, because once we make this something not involving a tangible everyday, set of objects, it's going to be a little more challenging in chemical terms. But hopefully you'll realize it's exactly analogous to this. Now, what if I told you that I went to a bunch of local junkyards and my haul today came back with in my trailer was 20 frames and 30 tires, and the question is, how many bicycles can I actually assemble? Well, in this case, 20 frames, that's enough to make 20 bikes. Okay, but 30 tires, that's only enough to make 15 bicycles. And I can see that I'm going to run out of tires before I run out of frames. And the one you run out of first, we call that the limiting reactant or limiting reagent. Same diff, totally synonymous. And so in this case, it's not the one you necessarily have less of, because I can see I have less frames. So it's the one that runs out first. And the reason it's not the one you run out, that you have less of, is because they don't always react in a 1-to-1 ratio. It also depends on what ratio they actually react with. So in this case, again, 20 frames, that's enough to make 20 bikes because it's a 1-to-1 ratio. But 30 tires, that's only enough to make 15 bicycles because of the 2-to-1 ratio. And so as a result, we're going to run out of tires first. That's going to be our limiting reagent or limiting reactant, as the case may be, and we're only going to be able to make 15 bicycles. Now, I'm not showing the formal calculation here because it's probably something that you can pretty much see in your head, but just keep in mind, because what we do with chemicals and compounds here in a little bit really will be totally analogous to this, with one extra little wrinkle or larger wrinkle that'll make it a little more challenging, but at its heart, the calculations will be very, very similar. All right, so the reaction we're going to deal with here is the creation of ammonia. NH3 is the formula for ammonia. And here we can see that 1 mole of N2 reacts with 3 moles of H2 to produce 2 moles of NH3. So here we've got a balanced chemical reaction. And my first question for you is, how many moles of nitrogen do I have? If you said 1, you're wrong. My next question for you is, how many moles of hydrogen, H2, do I have? If you said 3 moles, you're also wrong. And if I asked you, how much money do I have in my wallet? First correct answer you've had. You said, I don't know, Chad. How would I know? That's exactly the right answer. And it was also the same answer to the first 2 questions. How should you know how much hydrogen I have or how much nitrogen I have? What, you've been to my house and checked out, I've got tanks lying on the side of my house and you've measured how much nitrogen gas or hydrogen gas is in those tanks or something? So the point is this. When you see a balanced chemical reaction, it never, ever, ever tells you what you have. It only tells you the ratio in which things react. For every mole of nitrogen you do have, 3 times as many mole of hydrogen molecules will be required, and it will produce twice as many moles of ammonia. So it's always just a ratio in which things react. It doesn't have anything to do with how much you actually have. How much of anything you start with is extra information that's provided in addition to the balanced chemical equation. So first question here in this section says, how many moles of hydrogen gas are required for 6 moles of nitrogen gas to react completely? So we're told that I have 6 moles of nitrogen gas. I could have had any amount. I've got 6 moles of nitrogen gas. And the question is, how many moles of hydrogen gas do I need for it to react completely? And once again, I can see that 1 mole of nitrogen requires 3 moles of hydrogen to react completely, 3 times as many. Well, 3 times as many would be 18. And again, maybe you did that in your head. But formally, the process, which you're going to want to get down, because if the numbers aren't things you can do in your head and stuff, or things that you can't visualize quite so easily as this, then you're going to want to make sure you have that process down quickly. So in this case, I want to convert from moles of nitrogen to moles of hydrogen, and this is a mole to mole ratio, if you notice. And we said a couple lessons ago that there's 2 places you get a mole to mole ratio. One is from a chemical formula, but the other that we use in the limiting reagent context here is the coefficients in a balanced reaction. And the moles of hydrogen, that's where the 3 is, and the moles of nitrogen is the unwritten 1. It's a 3-to-1 ratio. And so in this case, we can see, just as we already predicted, that there are 6 moles of nitrogen are going to require 18 moles of hydrogen in order to react completely. All right, let's take a look at the second question here. So how many moles of hydrogen gas are required for 56 grams of nitrogen to react completely? And so this is one step more challenging, because instead of giving you the moles of nitrogen like we did from the get-go in the last question, I'm starting you off with grams. And the problem is that, again, the coefficients, those aren't a gram to gram ratio, those are a mole to mole ratio. So if I give you the grams, the very first thing you should do is get it into moles, because the ratios you've got are all mole to mole ratios, not gram to gram. All right, so in this case, 56 grams, first thing we'll do is convert it to moles, and the relationship between grams and moles is always the molar mass right off the periodic table. So in this case, we'll put grams of nitrogen on bottom, moles of nitrogen on top, and your molar mass is always for 1 mole. And if you look at the periodic table, be careful, this is diatomic. It's not just N, which would be 14 grams, it's N2, which is going to be 28 grams per mole of N2. And I rounded that to a whole number because nitrogen's really close to 14, so I round it to 14, and 2 times 14 is 28. And 56 divided by 28, we see that we've got exactly 2 moles of N2. And once I see that I've got 2 moles of N2, a 1-to-3 ratio, 2 moles of N2 would require 6 moles of hydrogen to react completely. So, but rather than stopping and calculating it and then converting it further, you can actually make it part of one big calculation. And so right now we've got moles of nitrogen, but we really want to convert this into moles of hydrogen. So we'll put moles of nitrogen on bottom so that they cancel. We'll put moles of hydrogen on top. And once again, that's our mole to mole ratio, that 3-to-1 ratio right from the coefficients in the balanced reaction. And 56 over 28 is 2 moles of nitrogen, and that 3-to-1 ratio tells me that it's going to require 6 moles of hydrogen. Cool, this is the wrinkle that can potentially make this just a little bit tougher, because everything in the balanced chemical reaction, it's a mole to mole ratio. And as long as I'm giving you moles and asking you about moles, this is no more difficult than the bicycle example we did earlier. But because we'll commonly give you, instead of the moles, we'll give you the grams of a substance. And instead of asking you about the moles of a substance, we might even ask you about grams as well. And so we might have had one more step at the end here. If I wanted to know how many grams of hydrogen I needed, well, then I'd have to convert this to grams. So, and it turns out it'd be 12 grams, because 1 mole of H2 weighs 2 grams. So then 6 moles would weigh 12 grams. It would have been one more step in the calculation, and it would have been a classic, what we call grams to moles to moles to grams type calculation. All right, so let's make this a little bit harder now. Now we've kind of got how this works, but essentially you can be asked anything about any ratio. I can relate any 2 species in the reaction to each other. So 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia. And so once again, let's say I told you had 10 moles of N2. How many moles of hydrogen would you need for it to react completely? 30. 1 to 3 ratio is a 10 to 30 ratio. How many moles of ammonia could that 10 moles of N2 produce? Well, based on the 1 to 2 ratio, the maximum it could produce would be 20 moles. 10 to 20 is the same as a 1 to 2 ratio. Again, you can compare any two species and use the coefficients from the balanced equation as your mole to mole ratio. All right, so now we're going to do limiting reagent calculations proper. And your limiting reagent calculations, we're going to give you an amount of more than one reactant, in this case, both reactants in this reaction. And you're going to have to figure out who the limiting reactant is and what's your theoretical yield and things of this sort. So in this case, I'm giving you that you're combining 112 grams of nitrogen and 30 grams of hydrogen together, and they're going to react to completion. And the first question is, who's the limiting reagent? Okay, well, you figure that out based on this 1 to 3 ratio. But that's a 1 to 3 ratio in moles, and you've got grams. And so the first thing you want to do is convert these both into moles to see which one you don't have enough of to match that 1 to 3 ratio that the reaction calls for. And so first thing we'll do here is we'll take our grams of nitrogen on bottom to cancel, convert that to moles of nitrogen on top, and 1 mole weighs 28 grams, molar mass right off the periodic table. Same thing for hydrogen. We'll put grams of hydrogen on bottom, moles of hydrogen on top, and 1 mole of H2. And one of the most common mistakes students make with a diatomic is they get that molar mass and they just use it right off the periodic table instead of doubling it. So this wouldn't be 1 gram, it's going to be 2 grams for H2. Those will cancel and we'll get moles in both cases. So the top one, 112 divided by 28, turns out is exactly equal to 4 moles of nitrogen. So, and 30 divided by 2 is equal to 15 moles of hydrogen. So things are looking a little bit different here. So a lot of students start this off and they're like, oh my gosh, we have way more grams of nitrogen than grams of hydrogen. So the hydrogen's definitely got to be the limiting reactant. Well, it doesn't work that way. So one, by the time you convert them to moles, they got very different molar masses. And it's not about who has more grams. It's partly about who's got more moles, but also what ratio do they react in. All those come into play. And so don't just look at whichever one you have the most grams of from the get-go and be like, he's not the limiting reactant. It's the one we have less of. Because it doesn't work that way necessarily. It could not. And if you've got a good chemistry teacher who wants to make sure you really know your stuff, they're going to give you an example, just like I have here, where if you make that assumption, you're going to be wrong. So be very, very careful here. Now, how do we actually figure out who's the limiting reagent here now that we know how many moles of each of these we actually have? Well, there's a few different ways. So my favorite is this, though, is to look at your balanced reaction, and I'll kind of explain it before we just kind of make it part of a process here. So in this case, every time we do this reaction, it takes 1 mole of nitrogen. Well, I've got 4 moles of nitrogen. So my question for you is, how many times can we actually do the reaction? Well, 4 times. Every time I do it, it takes 1 mole of nitrogen. I've got 4 moles. So I can do it 4 times. Cool. Now, I've got 15 moles of hydrogen gas here. So my question for you is then, if every time I do the reaction as written, it requires 3 moles of hydrogen, well, then how many times can I do the reaction based on that amount of hydrogen? Well, in this case, 5 times. So I have enough nitrogen to do the reaction 4 times. I have enough hydrogen to do the reaction 5 times. So then the question is, can I do it 4 times or can I do it 5 times? Well, I can only do it 4 times. So it's kind of like if I own a construction company and I tell you that I have enough bricks to make 1,000 homes with my construction company, but I have enough cement to make 2 homes. Well, can I make 1,000 homes or can I make 2 homes? I can only make 2 homes and I'm out of cement. I might have way more bricks, and we'd call that the reagent in excess. But once I've made 2 homes, I'm out of cement. That's my limiting reactant. I'm out. I'm done. I can't make any more houses until I get some more cement. Cool, works the same way here. I have enough N2 to do the reaction 4 times. I have enough H2 to do the reaction 5 times. Well, then I can only do it 4 times, and N2 is my limiting reagent. And the way I actually calculate this as part of a process, and again, this is not the only way. A lot of people would look at this and be like, well, it's a 1 to 3 ratio. So look at your 1 to 3 ratio, and you'd see that you're a little light. A 1 to 3 ratio would be a 4 to 12 ratio, and you've got more than enough hydrogen. And that's a valid way. There's nothing wrong with that. So, but students mix that up sometimes, and my favorite way that students mess up the least is just simply take the number of moles of each of these and divide them by their coefficient. So I'm going to take this one and divide by 1, this one divide by 3, just their coefficient from the balanced reaction. Whichever number comes out smaller is your limiting reactant. 4 divided by 1 is 4, 15 divided by 3 is 5, and so this is my limiting reactant. And notice when you divide by the coefficient, it effectively is telling you how many times you can do the reaction. So now we know the nitrogen is the limiting reactant. the answer to that first question. Cool. And I just wrote that out real quick because that's part of my process, but I don't actually use that as part of any future calculation. If I'm going to continue on from here, we're going to find out that these are the numbers I'm still going to work with, not the numbers after I divided by the coefficient. All right, so part B in this says how much NH3 is formed. Okay, if we look at how much NH3 is formed, so you always want to start with the amount of product you're forming, and technically this could be called the theoretical yield, by the way, from your limiting reactant, though. That's where you always start. So there's my limiting reactant. That's where we start. And so in this case, what you want to do is convert that to the moles of whatever you're converting to. In this case, I want moles of NH3, then you'll convert to moles of NH3. And you're converting from moles of N2, so that has to go on bottom. And notice that's a mole-to-mole ratio. And again, in this context, your mole-to-mole ratio always comes from the coefficients in the balanced reaction. Well, the coefficient for ammonia is 2, the coefficient for N2 is 1, and we can see that if we stopped here, that we would be able to make 8 moles of ammonia. Now, unfortunately, my question on the handout only said how much NH3 is formed. Now, if this were a multiple choice question on a multiple choice test, you'd look and you'd look at all the answer choices and you'd see what units they're in. Are they in moles? Great. Then you'd stop here and it'd be 8 moles. But what if all the answer choices were in grams? Well, then you have to take this a step further. Because my question only says how much is formed, I wasn't specific. But you're more likely to see a question that either says how many moles are formed or how many grams of ammonia, NH3, are formed. And so in this case, I want us to take this all the way to grams. But I just wanted to, I put it generic here on the sheet so that you'd realize there's 2 different ways it could be asked. But here, we're going to take it all the way to grams. And so we're not done yet. How do I get from moles of ammonia to grams? Well, again, connection between moles and grams is always your molar mass. And so right off the periodic table, nitrogen weighs 14, each of the 3 hydrogens weighs 1, and 1 mole therefore weighs 17 grams, rounding to the nearest whole number since they're all close to a whole number. And so now we're going to have 4 times 2 is 8, and 8 times 17. And again, you can use your calculator. It'd be a great time to do so, or you can do it in your head. So 8 times 17, 8 times 10 is 80, 8 times 7 is 56, and 80 plus 56 is 136. And once again, when you're calculating out how much product you can make, we call that your theoretical yield. Now, we call it the theoretical yield for a reason. So this is the greatest amount of that product you could make. But it turns out you almost never get that maximum possible amount. So usually you'll find that when you start mixing reactants together that there are side reactions that can happen. And so instead of doing this reaction, maybe these combine to form some other product as well. And because that will use up some of your reactants in making something other than your desired product, well, then you're not going to get up to 136 grams now. And so theoretically, that's the most I could make if everything goes perfect. So no side reactions. There's something else we'll talk about way later in this course called equilibrium, which comes into play. But this is the amount you get theoretically if everything goes perfect. And that's why we call it the theoretical yield. There's also something called your actual yield, which is if you actually go in the lab and, mix 112 grams of N2 and 30 grams of H2 and then measure the mass of ammonia that's actually produced. You actually did the reaction and that's how much actually got made. And we can compare that actual yield to that theoretical yield and see kind of how that goes. But we'll get there in a minute because we'll be asking that shortly. Third question for this set is how much of the reagent in excess is left over? And this is the hardest question in this section. And I say it's the hardest. It's not, all that hard in any other context outside of chemistry, but it will be hard here. So if we take a look at this, so the reagent in excess, the one that's going to be left over is this guy. And if you want to figure out how much of this is left over, you start in the same place you started out for your theoretical yield. So you start off with your limiting reagent. And we figured out right here that we got 4 moles of that limiting reagent. And so from here, you start with that 4 moles. And instead of figuring out how much product you're making, you're going to take that 4 moles of N2 and figure out how much H2 gets used up at the same time. Well, again, based on that 1-to-3 ratio and being that the numbers are nice, 4 moles of N2 would use up 3 times as many moles of hydrogen based on that 1-to-3 ratio, and that's 12 moles of H2. And so in this case, we can see that 12 moles of H2 get used. So we started with 15 moles of H2 in our container, 12 of them get used. And the question is, how much is left over? And you just take the number you start with, subtract off the number that got used, and you can see that you've got 3 moles of H2 left over, or we might say in excess. So it just doesn't react with anything, because by the time you've used up this 12 moles of H2, there's no N2 left in the container. Cool. Again, that's the hardest of the calculations on here, but it really just has come down to this process. So again, start with your limiting reactant, calculate out how much of that reagent gets used, and then just subtract it from the amount you started with. All right, last question in this section. Starts off with the same setup we just had. 112 grams of N2 reacts with 30.0 grams of H2. And it produces, like it actually produces, you went in the lab and actually did this, it produces 102 grams of ammonia, and the question is, what is the percent yield? So, and I want you to think about this in one other context real quick. Let's say I gave you money. I know you like this analogy. So, but I give you enough money to go to the store and buy me 10 oranges. I need 10 oranges. So I give you enough money to get 10 oranges, and you come back and you give me 8 oranges. And I'm like, hey, I gave you enough money to get 10 oranges. And I'm like, where's my other 2? And you're like, that's the tax for me going and shopping for you, Chad. I'm like, okay, fair enough. So my question though is, what is the percent yield of oranges? Well, I gave you enough to get 10. You only came back with 8. 8 out of 10 would be an 80% yield. Same thing here. Theoretically, we could get as much as 136 grams of ammonia, NH3. But in this case, we only actually got 102 grams. And so the percent yield is the actual over theoretical times 100. That is your percent yield calculation here. And so in our case, we actually got 102 grams of ammonia. Theoretically, we could have got a maximum of 136 grams. And this comes out to a 75% yield. Cool. These are all the questions relating to limiting reagents that you might see. Now, one thing you might notice, I used really nice numbers. I used numbers where we could do a lot of the math in our heads, and things of a sort, and this is a great place to start. But now you're gonna wanna get some practice, and you definitely wanna get some practice that's gonna deal with not so nice numbers. Because instead of starting with like 112 grams of N2, I could have been like, we start with 1.376 times 10 to the negative 4 grams of N2. And so you want to learn this process with nice numbers, but then you definitely want to work a number of examples with not so nice numbers to make sure that you really know this process and have it down pat. Now, if you've benefited from this lesson, consider giving me a like and a share. Pretty much a couple of the best things you can do to support the channel. And if you've got questions, feel free to leave them in the comment section below. If you're looking for the study guide that goes with this lesson, or if you're looking for a bunch of practice problems on limiting reagent calculations, check out my premium course on chadsprep.com.